Welcome to The Explainer. We're about to dive into a question so fundamental it sits underneath pretty much everything we think we know about reality. It is a puzzle at the absolute heart of modern physics. It sounds like such a simple question, right? But for more than a century, our two best theories of the universe have given us completely different answers. And here's the real kicker. They're not just different, they're basically at war with each other. So, on one side, you've got Einstein's general relativity. It paints this beautiful picture of a smooth, flowing fabric of space-time. But on the other side, you've got quantum mechanics, which describes this jittery, pixelated, chaotic world that's governed by pure chance. It's a total cosmic contradiction. So, how do you possibly unite them? Well, a new theory suggests maybe we've been starting in the wrong place this whole time. What if space-time isn't the foundation of reality at all, but something that actually emerges from a much deeper level? Okay, so this brings us to a really radical new idea called NQS geometry. Now, I know, the name's a bit of a mouthful, but the concept behind it is revolutionary. It's basically proposing that space-time isn't the fundamental stage where reality happens. Instead, it suggests that space-time itself just pops into existence from something way, way deeper.
What this means is we kind of have to throw out our old map of reality, this whole idea of a pre-existing stage, this God's eye view. We're going to try something completely different. We're going to build the universe from the inside out, right from the perspective of an observer who's actually in it.
So to really get how radical this new map is, we need to do a super quick recap of the old one. You know, the geometry we all learned back in school. Classical geometry, the kind we're all used to, is built on a few really basic ideas. You've got points, which are just fixed locations. You've got distance, which you measure with a ruler. And you have curvature, which is just how space can bend. It's a very intuitive, outside-looking-in view of the world. NQS geometry just flips this whole thing on its head. It tosses out those old ideas and replaces them with something totally new. So instead of abstract points, it starts with contexts. Instead of a ruler for distance, it uses something called the cost of change. And instead of simple bending, it has this idea of questioning loops. It's a whole new geometry built not on abstract space, but on actual observation and interaction. And this is the crucial shift. We're not starting with some abstract grid of points anymore. We are starting with you, the observer, in a very specific situation. A context is just your immediate reality. It's what you can see, what you can measure, and what you can do, right here, right now. But hang on a second. If we've thrown out the ruler, how in the world can we talk about something as basic as distance? This is where the theory gets really weird and, frankly, brilliant. It all comes down to the idea of cost. Here's the core idea, and it's a wild one. Imagine a spinning top, just perfectly balanced, totally stable. Now, you try to nudge it. The distance to its new wobbly state isn't measured in inches or centimeters. No. It's measured by how much effort it took you to push it, how strongly it resisted your change. In this new geometry, that resistance, that cost of changing it, that is distance. Now, the fancy math behind this is called a self-preservation functional. Don't worry about the name, just think of it like a stability score. Every system in the universe is basically trying to get the highest stability score it can. Or, to put it another way, it's always trying to find the path of least resistance. So a system that really fights back when you try to nudge it, one that has a high stiffness, is by definition considered far from the state you're trying to push it into. The geometry of our universe, in this view, is really a geometry of stability. All right, so now we can finally tackle the last piece of our new map, curvature. Now, classically, curvature is just about how space bends. But in this new system, it's about what happens to you when you take a journey through a bunch of different contexts. Just picture this. You start out in one situation. We'll call it context A. Then you move through a series of other situations. Context B, then C, and then finally you come back to where you started. You'd probably assume that once you're back where you started, everything would just reset, right? It'd be exactly as you left it. But in this new kind of geometry, that's not always true. See, in a flat space, you'd come back totally unchanged. It's like walking around a city block and ending up exactly where you started, facing the same direction. But if there's NQS curvature, the journey itself actually changes you. Even though you're back in the same spot, your internal state has been permanently shifted somehow. And that leftover change from your journey, well, that is the definition of curvature. It's a measure of how the path you take affects who you are when you get back.
So why on earth would we go through all this trouble to redefine geometry from the ground up? Because, and I am not exaggerating here, if this theory is right, the payoff is absolutely mind-blowing. So here it is, the most incredible claim of NQS geometry. You don't need to add in the laws of physics by hand. From this really simple framework of just contexts, costs, and these questioning loops, the laws that govern our entire reality, they just emerge. They're an inevitable consequence of the geometry itself. And the results are just astonishing. That weird definition of distance based on the cost of change, it turns out that naturally gives rise to the fabric of space-time and the force of gravity. The unique built-in properties of each context, its internal symmetries, its fundamental character, that gives us the forces of the standard model, things like electromagnetism. And those questioning loops we talked about, where the journey changes you, they become the very curvature of space-time that Einstein described. It all just falls perfectly into place. And this suggests something amazing, that our two great conflicting theories, general relativity and quantum mechanics, they might not be in conflict at all. They could just be two different views, two different charts of the exact same single underlying reality, this geometry of stability. This leaves us with a pretty profound final thought. What if we've been asking the wrong question all along? We ask, what is the universe made of? But maybe the universe isn't made of stuff at all. Perhaps reality is just the inevitable result of systems finding the most stable way to exist. What if everything we see, from the smallest particle to the largest galaxy, is just a pattern in this endless, elegant, cosmic drive for stability? It's a pretty incredible thought to end on.